Anyone recognize John Oliver screaming in the background? That's my husband watching TV. Anyway, so null spaces, column spaces, and linear transformations. So we have some more definitions for things. More names, same stuff, different day. So the null space of a matrix, we call it NUL of A, is the set of all of the solutions of the homogeneous equation AX equals 0. So as remember, our homogeneous equation always has a solution. 0, 0 might be the only solution, but it also could have an infinite number of solutions as well. So we want to find, is U, in this example, so is this vector in the null space? In other words, is it a solution? So is a U equal to the 0 vector is essentially what this question is asking. So all we need to do is take A times U, so our 1, -3, -2, -5, 9, 1. We're going to multiply that by 5, 3, -2. Pause here if you want to, but fun fact, hey, we get 0, 0, which is, so yes, that is in the null space. So yes, U is in the null of A because it is a solution, or it is a solution to that homogeneous equation. The null of A is a subspace of Rn. So notice here you see that our this is a 2 by 3 matrix, and our, oh, I totally fudged that up, didn't I? No, I didn't. Oh boy, did I? Maybe? No, I'm good. This is a 1 by 3, a 3 by 1 matrix. So this is a 2 by 1 matrix. Did I do that correctly? Right. We're talking, this is in our subspace, right? This is a 3 by 1 matrix. So this is in R3, which means that this is, anyway, okay. Oh boy. Another way to say that is that the system has n of m homogeneous linear equations with n unknowns is a subspace of Rn, right? So this has 3 elements, so it's a subspace of R3. Okay. We're going to let H be the set of all vectors in R4 whose coordinates A, B, C, D satisfy the equations A minus 2B plus 5C equals D and C minus A equals B. So if we use this definition, this theorem here, we can say that if I can get the homogeneous equations, so we want to show that H is a subspace of R4. So all we need to be able to show is that I have m homogeneous linear equations and I have n unknowns. So my first one, if I write this as a homogeneous equation, it's A minus 2B plus 5C minus D equals 0. And the next one would be, and I'm going to rearrange it so that my letters line up. So I have minus A minus B plus C equals 0. And if I write this as a vector equation, you ready? I'm going to take the coefficient matrix. So I have 1, -2, 5, -1, -1, -1, 1, 0. And my X matrix is A, B, C, D. And this is an element, so this is an element of R4. And we've said that it equals the 0, 0 matrix. So yes, by that theorem, yes, H is a subspace of R4, right? Because the null space, so in other words, this guy right here is our null space, right? The null of A is equal to A, B, C, D? Any of those solutions? Anything that makes that true is in the null of A? Yeah? Yeah? Makes sense? Hopefully? Do-do-do. 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 Yeah. Ta-da! There we go. All right. We're going to do some fun matrix. Do-do-do. Okay. We're going to find the spanning set. So notice I didn't ask for the span. I asked for the spanning set. So I asked for a set that represents the null space of A. We just said that the null space of A is all solutions such that A, so the null of A is equal to all of our x's, our x vectors, that satisfy AX equals 0. All right, that's our null space. So we're going to set up our matrice to solve for the homogeneous equation. So you ready? I'm going to set up. So -3, 1, 2, 6, -2, -4. You know, sometimes I like to go down by columns. Sometimes I like to go across by rows when I write it. Sometimes. So what I'm going to do is I am going to reduce this to its RREF form. And I'm going to, for the sake of brevity, I'm going to let you do this on your own and see if you come out to these. So pause the video, do your row operations, come back when you think you're in RREF, and compare. How'd your RREF go? So hopefully you can now see. So if I want to find the null space, that means I want to find all the solutions, which means it's actually going to help us to write the solutions in parametric vector form. Because then I can write the solutions as a set of, so as a span, right? So first thing I'm going to do is I'm going to write them out. So we can see, so here's a pivot position, here's a pivot position, which means that we actually have 3 free variables. So 3 free variables. One of them is x1 or x2, one of them is x4, and one of them is x5. So if I write the description, just the parametric description, I'd have x1 is equal to 2x2 plus x4 minus 3x5. We said x2 is free, so x2 is equal to itself. x3 is equal to negative 2x4 plus 2x5. x4 was free, so equals itself, and x5 was also free. So if I take this idea and I write it in parametric vector form, right? So in parametric vector form, we have that the vector x1, x2, x3, x4, x5 is equal to x2 times whatever constants that end up in, so in x1, x2 is multiplied by 2, x2 is multiplied by 1, in x3, I've got no x2 term, and same thing with the last 2. And then I have x4. So again, is all my free variables times their associated vectors. So I've got a 1 in the first one, no x4s in the second equation, minus 2 in the second one, third one, one of them, and then none of them. And lastly, we have x5. And x5, we've got minus 3 of those, none of them, 2 of them, none of them, 1 of them. Hey. So the null space here is the set of all solutions to this equation, and the solutions to this equation are, remember we talked about the linear combinations that make this true, which is also our span. So the null space here for A is equal to the span of, I'm going to call this vector 1, vector 2, and vector 3 instead of rewriting them. So it's the span of vector 1, vector 2, and vector 3. So, ta-da! All right, so column spaces are like null spaces, but different. They're similar. So a column space actually does involve a span, whereas this one, in terms of the reason this works, is that if I take any x2 or any x4 or any x5, then that is going to give me a solution to, so this span is equal to all of the x's, that make ax equals 0 true, right? Because if I pick any x2, x4, and x5, I can backtrack and get x1, x2, x3, x4, x5, right? And that's what these vectors represent, right? The span represents, this is the linear combo of these vectors. Now, it's going to sound like I just said that and that the column space is going to sound exactly the same as that, but I promise you they are different. The column space is what happens when you take the linear combinations of all of the columns of A. All right, so you'll notice these here, those are not columns of A. They are vectors. It is a span of vectors, but it is not the same span of vectors that we're talking about for the column space. So the column space is the span of the vectors that make up the columns of your A vector. So it turns out that these are actually solutions to the AX equals B equation, right? Which is fun. Yay. This is all of our B's. So we're solving for our B's, which means the sizes of these things is different. So remember, our theorem here says that our null space theorem said that the null space was a part of Rn. The column space is a subspace of Rm, right? Because again, if you think about this, if we're trying to find the things of B, if A is a 3 by 2 matrix and X is a 2 by 1 matrix or vector, right? Is a 2 by 1 vector, then B is a 3 by 1 vector. Hey, by 3 by 1, right? Here's our M. Here's our M. This is 3 by 1 is an element of R to the M. Hopefully that makes sense. So different subspaces of different vector spaces is what happens when we do a column and a null space. So we're going to compare and contrast these things just to kind of prove or show you and sort of hammer in the point that these things are not the same. The column is a subspace of, so this is a 3 by 4 vector. The column space here, again, is what happens when we take each of these vectors and we find the linear combination of these things. And if you think about it, if I have some x1, x2, x3, my resultant vector, I need another one, x4. My resultant vector here is going to be a 3 by 3 vector. So I'm going to have ABC here, right? Because I have 4 times, this is a 4 by 1, this is a 3 by 1, which means that the column space here is a subset of R3. The null space, however, is talking about what happens when this thing is equal to 0, 0, 0. And what we're talking about in this case is our X vector. So the null space here is a subspace of R4. They're not the same. right? So not the same. They're not equal. So they are not the same subspace. They're not even within the same vector space. But, this shouldn't say subspace. This should say vector space. So what would have to be true for A in order for our column and our column space and our null space to be in the same vector space? So I'm not saying they're the same subspace. I'm saying they'd be in the same vector space if it's a square matrix. Right? So we've already... Hold on. Good Lord, she'd bark at a mouse fart. Okay. Right, we said that the column space, so the column space of A is an element or is a subspace of Rm. The null space of A is a subspace of Rn. So if my matrix is an n by n matrix, then both of these things become Rn. So they're both subspaces of the same vector space, but they are not necessarily the same subspace. Hopefully that makes sense. With me? You with me? All right. We're going to come back in another video to talk about a little bit more about the contrasts, and then we are so close to done.